Today we're going to learn how to do a hypothesis test using one-way analysis of variance, or ANOVA, how it was what it's usually called, using our 6-step process. Now, an ANOVA test is usually used when you have more than 2 samples. And so 3, 4, you can have as many samples as you want when you're doing an ANOVA test. The requirements for this test is that the samples are random and independent, and the population must be normally distributed. Now, the hypothesis statements look something like this, where the null is that all of the means for however many samples there are equal. And the opposite or inverse of that is the alternative that, well, at least one of them is different. So I can't say which one is different in a hypothesis test using ANOVA. I can just say that they're not all the same in that alternative statement. Now, either one of these can be the claim when we're doing these problems. Now, I always need a standardized test statistic to find the p-value in these tests. We're used to using t when we're dealing with means, but we're going to be using a different distribution in the ANOVA test, and that's the F distribution. This one's a lot different from the t distribution and the standard normal distribution that we are used to using. They're not necessarily symmetric and bell-shaped. The curve does vary depending on the test, the values in the test. So we're not really going to look at pictures of these when we do the test. It's just not worth the time. And I'm not even going to show you the formula for how to calculate F, because we're going to let our technology do that for us. I'll show you how to calculate the F statistic and the p-value using both the calculator and Excel in our example. Okay, so here's an example, kind of a long one here. Precision weighing devices are sensitive to environmental conditions. Temperature and humidity in a laboratory room where such a device is installed are tightly controlled to ensure high precision weighing. I'm already a couple sentences in and I haven't gotten any useful information for as far as coming up with the answer, but I'm going to keep going. A newly designed weighing device is claimed to be more robust against small variations of temperature and humidity. To verify such a claim, a laboratory tests the new device under 4 settings of temperature humidity conditions. The 4 experimental settings are defined and noted as T and H, as in the table. So if we look at the table, I can see we have high and high for our first sample, so high temperature, high humidity. The second sample, high, low, so that's high temperature, low humidity, and so on. A pre-calibrated standard weight of 1 kilogram was weighed by the new device 4 times in each setting. The results in terms of error in micrograms are given. Using a 1% level of significance, test whether the data provide sufficient evidence to conclude that the mean weight readings by the newly designed device vary among the 4 settings. Assume the population is normally distributed. Okay, so that second to the last sentence is where my claim lies. And so we want to prove that the means vary at the 4 different settings. So my claim is the mean weights are not all the same. And then the alpha we were given was 1% or 0.01. And that's really all the data that I'm going to collect in this first step. I'm going to be entering all this data into either my calculator or Excel in order to do all the calculations. So there's really nothing else I need in this first step. So in the second step, we go ahead and put that claim into our hypothesis statements. There were 4 samples, so the null is that all 4 means are equal. So mu1 equals mu2 equals mu3 equals mu4. And the alternative was our claim that at least one mean is different. In step 3, we want to state the test. So this is an ANOVA test. If we want to remind ourselves of the distribution, we can add that in there. So ANOVA F test, because we're using an F distribution. And luckily, at the end of the problem, they did tell me I can assume the population is normally distributed. So I have met the requirements for this test. In step 4, now I'm ready to calculate that F statistic. And so if I'm using a graphing calculator, I am going to find the ANOVA test in the test list and just list out all of the lists of data that I have entered into the calculator. So let's pop over to my calculator and see what that looks like. So if I go to Stat and choose Edit, I can see here are my 4 data sets listed in lists 1 through 4. And so now I'm going to go back to Stat, and I'm going to go over to the test list. And there's a whole bunch of tests here. ANOVA test is at the very end. So I'm actually going to just click up, and it will wrap around to the bottom of the list. So I don't have to scroll all the way down to this one. And I can see H here is ANOVA. So I'll choose that one. And now it's just waiting to know, well, how many lists does it need to include? And the lists are listed above the numbers here. So I'm going to do list 1, so second 1, comma, and then list 2 is above 2, comma, list 3, comma, list 4. So I have all the lists of data, close off the parentheses, and hit enter. And there's my F statistic, about 9.602, and my p-value as well, 0.0016. Now it gives me a lot of other information, but again, if all I'm doing is this test, I don't really need to grab any of that other data that it calculated. So I have an F statistic of 9.602. Now if I want to do this in Excel, this is a little bit more work. You're going to need the data analysis add-in, which I've got a whole other video to show you how to get that add-in in Excel. So for now, I'm just going to assume you've already got it. So here's my same set of data in Excel. To get to the data analysis add-in, once you've added it, you go to the data tab at the top, and it should be over here on the far right, data analysis. And so this has a list of a whole bunch of tests that you can do if you have actual data sets. We want to choose the very first one, ANOVA single factor. And now it wants to know where the data is that it should be testing. So come over here, I'm going to highlight everything, including the labels at the top, which is not required. Because I highlighted the labels, I want to check this labels in first row box. My data is organized in columns, so I choose columns from grouped by. Alpha is 0.01 for this one, so I'll change that. And then where the test gets outputted, I'm going to click output range so I can decide where on this sheet it goes. And so I'm going to stick it over to the right here and click OK. And just like the graphing calculator, this does give me a whole bunch of information. Really, the only things I really care about here are the F statistic, which I can see matched what the calculator gave me, and the p-value right there. The rest of it, I don't really need to complete my hypothesis test. Okay, so I've got F, and I also have P in step 5, 0.0016. And if I compare that to the level of significance, the p-value is less than 0.01. So in my last step, I can go to my table to make my decision. When P is less than alpha, I reject H0. And the claim was in the alternative, so there is enough evidence to support the claim. And so I'll just throw the claim in there in my final statement. There is enough evidence to support the claim that the mean weight readings by the newly designed device vary among the 4 settings. And that is it for an ANOVA test.